Welcome. First of all, I'd like to thank everybody here. We're really thrilled and really excited about doing this presentation because, well, in our country it's one of the first developments of mission concepts based on nanosatellites and especially on CubeSat mission. So let me begin with some background and inspiration, and it comes from really not so much time before that we learned about what tech maps were in some couple of conferences, and I started to wonder how do they work and why are those important. And we started to do our research, and we've found out two important things. The first one is shown in this picture. You can see a lot of ground systems that are the ones that measure the status of the ionosphere, and they create the tech maps. And as you can see, they are located in this example in USA, in Canada, but here is Mexico, as you can see. And we have none. So we do not generate that information. And we were doing some research about it, and we found out that indeed we do not have the technology to make this kind of ionosphere observation. And this is where the idea came. How can we generate this data? And we were really into developing some kind of small satellite systems, and we thought that it would be a really good idea to put something up in the sky, flying at a certain altitude into the ionosphere, and to in situ measure the status of the ionosphere in order to get some data, and well, thoroughly do a lot of research about it into the telecommunications range in Mexico. So another thing that inspired us was these numbers here that are the monthly passenger traffic in two of the most crowded airports in Mexico. The first one is from Cancun, and the second one is Mexico City International Airport. And as you can see, there is 1 million passengers traffic monthly in sort of both of them. So there's a lot of big traffic, so these are really crowded airports, and we were doing some research about, and why is this important? Because the information of that you get from the tech maps and from the ionosphere status and stuff is really important for the GPS calibration and the GPS information, and also for the inner communications on Earth. And you know, with this amount of traffic, the importance of having accurate measurement systems of everything that can affect telecommunications is really critical. So that was another point of inspiration to try to develop this project and to generate this idea. And well, this is another chart when we can see the big growth between 2015 and 2016 comparison of the passengers traffic in the airports, and we can see that it's even increasing. Actually, in Mexico we are starting the development of a new international airport in Mexico City, so this is going to be really useful. We need to have this kind of information, this kind of systems. We were doing a lot of research about how do we get this data, and we have to acquire it from other systems, and we don't have any local system. So I was thinking, why shouldn't we have a local system to do this kind of research and to, well, give a good use of this data? So this is it was mainly our inspiration for the development of this project, and we settled two main objectives. The first one is to design a CubeSat nanosatellite-based mission for the measuring and qualification of the total electron content in a determined location of the ionosphere. At a determined location, it will be like a certain height. And I will explain later how did we decided to put this mission into a certain height. And the second one was to design a proper array of ground stations enabled to receive and process the data obtained from the CubeSat measurements in order to generate, and that's the main goal of all of it, in order to generate regional tech maps over the Mexican territory. We want to deploy this system, this idea, in order to generate this information for our territory, but of course it can be expanded to be useful for any other places and any other countries. because the CubeSat will be doing a lot of rounds around the air, so it's not to be selfish, but the main goal is to use it for ourselves, but maybe in a certain future we'll share this information for some other country that would need it. I'd like to show you, I'm starting with this because we wanted to, first of all, do a design, a concept design of what would a CubeSat designed by us would look like. And we decided to choose a standard 3U CubeSat because of many reasons. The main reasons were like we have to deploy some instruments, some measurement instruments, and I gotta be honest, at the beginning when we got this idea, we developed it, and after we developed the idea, we started to think, and how can we do these measurements? And that's the reason why we found these little things, these two little things, that are actually our concept or our idea to use line width proofs. In previous sessions, a lot of people have talked about the line width proofs and how they are used and what we can do to measure these plasma environments like the ionosphere. And we thought that it would be a really great idea to implement two line width proofs as our main payload. So the entire bus satellite would be as I tell you, a standard 3-unit CubeSat, and our payload will be using the line width proofs, and well, these ones are just the antennas deployed. And so we started to think about our payload design, and we went to a really simple proposed block diagram for the payload that it consists in our two instruments. It's a really basic and raw proposal, but I think it's really useful for us to understand what we are going to do. So it's to take our two proofs as our main sensors and do an instrumentation process that would have the specific electronics that will do the instrumentation for the variation from the current that the proofs will deliver, and using low gain instrumentation amplifiers and high gain ones, and through a multiplexer to the ADC of the microcontroller. And also we're proposing that the payload should have its main microcontroller different from the OBC computer, of course, because it has to be really focused into only processing this data. This is a proposed block diagram, and that's what we are starting to work with. And of course we have to design a power and a mass budget for this mission. So after we decided that we wanted to do this mission, well, we have to start looking and searching for what does the bus satellite would contain. So the approach we're taking is a COTS approach, because we're really new into this kind of developments, and we want to focus into the mission and not into the bus satellite design. So what we're going to do is to look for the best suitable and also affordable subsystems that we can buy, that we can integrate, and that we can put together in order to achieve the goals for the mission. So for the mass and power budget, we're taking the information and the parameters from commercial components. We are not designing any of it. We are only going to focus into the design of our payload. So, and after that, we have to have a link budget, because it will be communicating to the ground, and it's actually, it's not an entire link budget, because it's only taking into consideration the total time to download one payload frame plus the telemetry frame that the satellite will be generating and sending back to the ground station. I know that this is not like truly well done, but it was useful in order to get this time in order to start the design of our orbits and where to put our satellite. And this is when I want to focus just a little bit more. We decided to use a sun-synchronous orbit. Maybe you will realize that between the abstract and the final paper, we changed entirely the orbital design. And the reason why is that when we first designed our orbit, it was like, okay, we can deploy it from the International Space Station, and we will have even though we have the drifting, it's okay because it will be drifting and we'll be doing a coverage of the entire Mexican territory. But afterwards, after we sent the abstract and stuff, we started to do more research, and we realized that it was not a really good idea because the times of every pass, when they repeat, they wouldn't be repeating at the same hour, for example. And we were like, well, the data that we get on some certain spot won't be reliable and won't make any sense if we compare it from the one that was like 2 o'clock yesterday and today is like 3 in the morning. So they didn't have any relation. So the sun synchronous orbit gave us this really good chance to have synchronized measurements. So every time we can measure one pass through a certain spot, we will have the sun synchronous capability to actually have the ability to compare this data from the day before to the day we're taking another one. So we could have like a parameter where we can compare results and actually do some research about our result, the result that we are getting. So as we can see, the orbits per day, according to the height we are putting the satellite and the maximum latitude, this is really interesting because our calculations were established in our sun synchronous orbit, and sorry, not one. Yeah. Okay. I don't know why it get the jump. Well, whatever. In the design of our orbit, our results showed us that at an altitude of 300 kilometers, all the reps per day would be like 15.88 reps every day. So this is the amount of circles that the satellite will do through Earth. And we decided to use the 300 kilometer parameter. Why? Because when we started our research, we were looking into different repositories of tech maps, and we saw the one from the JPL, and we saw that information. And because of this is a first approach of a long research of the ionosphere, the first thing that we have to do is to get the data and to compare it to current research like the JPL tech map. So we looked into some information, and we found out that the altitude of measurement of that tech map was at 300 kilometers, and that's exactly the reason why we choose to put the satellite in the exact same spot in order to try to replicate the results and to compare them and to have a start point in order for us to achieve some good research and to at the end have reliable data. Okay. And this is the simulation of the orbit, and as you can see, this is Mexico, and this is our this is a single ground station because we started with just one single ground station, and these are the passes of the little Ion CubeSat. That's the title of our mission, and it covers all this area, and this is from the receiver to the satellite. This is the time axis per orbit, and as you can see, we will have at certain points a lot of time to receive, and at some other points we will just lose all that information. So we have the duration of the time axis from the receiver to the ground receiver to the communications antenna from the satellites, and all the orbits that it will be doing, 1, 6, 11 and stuff. And that's why we needed to also know how much time would the data will, how much time of watching the satellite we should need in order to gather all the information every pass, because we are doing measurements in situ, and we have at every pass we have to get the chance to download all the data in order to create a good repository and to have reliable data. If we don't do this, it won't work. So after that, we now can go to propose all the ground stations, because if we are stuck with the Mexico City, I will have only 2 to 3 passes per day, and it's all the data that we're gonna get. So it's also not really reliable to have only like 2 or 3 passes a day, and that's all the data we're getting. So the other part of the proposal is to set a network of ground stations And we selected these ones because of two reasons. The first one, they are located like all around the Mexican territory, and the second one is that every ground station in every one of these states held a big university with some research on engineering, so it could be a good idea and a good proposal for them to make the investment into the development of the ground stations into their facilities, so we could achieve a good networking and a good work between universities, because we come only from two different universities, and it would be like a good way to share knowledge and to make the implementation easier, because if we work alone, we know that we wouldn't get like anywhere. So we have a proposed schedule, because we need to do a lot of research and a lot of development, but well, for the next year it will be entirely for funding, because we are really don't have much funding, so we have to do a big campaign of funding through the next year. And after getting the funding, we will start our design development, integration and testing deployment, and in 2018 the main idea is to develop our engineering model, and afterwards the finish of 2018 and the beginning of 2018 start with all its testing and the further development of a flight test. We know that we can take even longer, but our idea is that in 2 years we have the entire time to do our engineering and flight model development and also the testing. And so in 2020 the launching campaign, and it will operate for we're intending to launch it like in the middle of 2020, so it will be working for more or less 2 or 2.5 years, and after that we have a disposal proposal that we haven't started, because well, actually here we have learned a lot about the orbiting technologies, and we now realize that it's really important to include this into our design. We will plan it, we will see how we can achieve proper deorbiting, but at the time we don't have any idea of how to deorbit it. So another thing to consider was our launch options. And we do some research into the user's guide rockets in order to see who could achieve a proper launching. We saw several options, but the most reliable would be using the Atlas 5 gear, also by a proposal of a piggyback, because you know, if you just arrange one launch with an Atlas 5 just for one CubeSat, it will be like tremendously expensive, so we will have to look for a good campaign. And actually one idea and one proposal we have is with the Mexican government in order to for the next Mexican satellite for telecommunications to launch, try to do some kind of arrangement in order to get a piggyback launch of our CubeSat and maybe some other academic CubeSats to achieve this. And well, the best option is the Atlas 5 thrown by the Vandenberg spacecraft, because of the inclination and the characteristics of the orbital design. And well, we have a lot of risk. The possible, actually I think it's not possible, it's every risk is possible. Maybe this should be changed to the most critical risks. And the first one will be the funding, because we currently doesn't have it, or the little funding that we have is not enough, so we will have to put a lot of effort into our funding campaign. Another will be the delay of delivery parts from vendors. For example, we have to buy, after we got the funding, we have to buy some craft or some specific design, and we have to pay for a customized design. Maybe if we are really short on schedule, we will have a lot of trouble. Of course, the success of missions operations in space, because it will be the first time for us to put something in space, and we have almost zero expertise in this area, so it's a really critical risk. Regulation for smart satellites, at least in Mexico, it's only on development, so we have to do a lot of research of the regulations, the telecommunication regulations in Mexico, and of course the launching opportunity loss because of the critical orbit that we're designing. Just to conclude, because I'm almost over time, the development of a multidisciplinary work is what we were developing because it was three of us from different universities. One of the first developments of nanosats in Mexico, that's exactly what we are doing. We have to also get a mission success criteria because we cannot be sure that it will be like 100% reliable. And of course, integration against full development. We're doing integration, we're using COTS because we're just getting into this network. And this was our work distribution between me, my partners Antonio and Carlos. Everybody put some effort, and well, just to finish, the three of us. Thank you for your attention, and I would like to thank our sponsors and our universities and our Ministry of Telecommunications and the Mexican Space Agency that made possible that we are standing here right now. So thank you very much.
What is your mission life? How long do you want to be in orbit?
We want to be in orbit for at least 2 years. 2 years in orbit.
Okay, but orbit altitude of 300 kilometers, you may be in orbit just for 3 weeks. It's too low.
So, it's too low for...
Yeah, your drag you will deorbit very quickly.
Sorry?
You will deorbit very quickly from 300 kilometers.
Okay. So we have to do a lot more research.
Either you need a propulsion system to maintain your 300 kilometer altitude, or you will have to raise the altitude.
Okay.
Yeah, I think that is the main point. And you're on a conceptual phase, and it's just your kind of strawman design you are doing. But this remark is an essential one. You will end up with another size of your CubeSats.
Okay.
And for the motivation part, at the beginning you showed a view graph with the airports and the traffic on the airports, and Guadalajara was the third highest traffic, and in the ground station distribution you showed, Guadalajara didn't show up. So I think there is some mismatch between motivation to do something to improve the measurements in certain areas, for instance the airports, and then having the ground stations somewhere differently.
Yeah, actually, let me just check the list. It's here. Yep, of course. Well, actually, the center. We should probably change one spot from Sinaloa to Guadalajara because you are absolutely right. Guadalajara is one of the most crowded airports, of course. But we were approaching mainly the Cancun and the Mexico City airport, and for the other ones, just to make an approach through the main university that do this kind of research. But it's a really good suggestion, and I think you're totally right. We have to match more the motivation and the work we're trying to develop. So we'll take it in real consideration.
It's more a formal aspect, but it is.
Yeah, of course. Thank you.
One question again. I understand you're at the straw, very preliminary design phase, but it wasn't clear to me what the requirements for your sensors are. Like you had attitude control requirements. You had an ADC system that you were putting in, but the question is, do you need it? Is your linear probe? Do you need to know the orientation very well? Do you need to point it in the right direction, or you just need to measure?
Actually, this is a really good question that we were also in the morning discussing about that. As we know, we've done a little research about the language proofs, and we haven't actually settled down if we will need an important pointing in ADCS system in order to get them straight, or if it's okay that it can be rolling, for example, that it won't affect the measurement. There's something that we haven't researched properly, and even less made in the test. So it's also taken under consideration. For this first approach, we are not paying attention into if it's rolling or not. It's only doing the measurements right. But if we discover and we determine that we need the language proofs to be stabilized, well, we have to add a more powerful ADCS to the CubeSat. But yeah, we're taking it in real consideration. But we have to do our research first to determine it.
Okay, so I'm asking about tech maps, and so who may be the primary customers to use this map? And the another question is that if this customer will, in future, will pay continually the funding to develop your satellites?
We believe that the information from the tech maps it's used by the airports. They use this information. I did my research, and they buy this information from the systems in USA and some others. I think in Europe. I don't remember, but they were really into the USA acquirement of these tech maps. And we didn't have a lot of big discussions for the authorities of the airports. Well, what we were really clear is that they would be our primary customers from this information.
So it's time to move on to the next presentation. So thank you.
Thank you very much.